introduce Dr. Anthony Difranzo here. So Anthony did his PhD work at UC Irvine. During this time, he spent some time at Fermilab on a kind of graduate theory fellowship type thing. He spent most of his time doing dark matter model building, and he's going to tell us about some of that today. So
thanks. All right, thanks for the invitation, and thanks for the opportunity to escape winter for a few days. So as you just heard, I'm going to talk a little bit about dark matter model building. In particular, I want to focus on dark matter that mainly interacts with tops. And so the work I'm going to be talking about was done also with Matt, Angelo, and David, who are also at Rutgers. And so you should be expecting a paper in the next few weeks. So just to give you an idea of where I plan to take us during this talk, I want to start out by talking a bit about how current dark matter searches work at the moment, and just the canonical thought process that people go through when they're trying to build a model. I'm going to talk a little bit about motivating top-philic dark matter with a little bit of experimental and some theoretical reasons of why you might be interested in this. And there'll also be some talk about what models I in particular will be interested in, and I'll give you some results for those models. There's also a little bit of an excess along these lines, which I'll talk about at the end if there's some time, and then we'll conclude. So of course, I'm going to start off with everyone's favorite picture of dark matter complementarity. The premise that underlines almost all dark matter particle physics is that it has some interaction with the standard model. So assuming that it looks something like this, in this diagram, if I read it in one direction, I see that something in the standard model can scatter off of dark matter. That same thing comes out, and dark matter comes out as well. So this would be direct detection, where I have some large vat of nuclei, and I'm waiting for dark matter to bump into one of them. If I rotate this diagram and go up, then I see that I'm also able to take two dark matter particles, push them together, and produce something in the standard model that I can actually view. So you would be looking somewhere in space where I know there's a lot of dark matter and I could benefit from this process. Or lastly, which collider physicists or particle physicists in general are always excited about, is taking two things in the standard model, smashing them together, and actually producing dark matter ourselves. So that'll be collider physics. One thing I want to focus on is that this is really just a cartoon. There's no model-independent way for me to rotate this diagram and expect that to be the main thing I'm looking at for that probe. So whenever you see multiple probes, limits for multiple probes plotted on the same plot, you should be a little skeptical and should know that all those probes come with some caveats. What are they actually interested in, and how are those probes actually related? And it's not always just as simple as rotating this diagram. So since they all come with caveats, let's run through the main probes really quickly and just talk about what caveats could be there. So first, collider search. If I just take two protons at the LHC and smash them together and dark matter comes out, I would never know that that had happened, right? If nothing comes out, I don't realize that it happens unless I precisely know how many protons are coming in and coming out from my beams. But what if something else pops out from that interaction as well? And let's say that X is something in the standard model that I can actually see in the collider. Because I know what the transverse momentum in that process is, I know that if something comes out, it better be, I know if only one thing comes out and the transverse energy isn't zero, then something else must have been there. So you can tell that it's there just by the fact that you know that energy and momentum are conserved. And so this X can be a whole bunch of things. So these are usually cataloged in what's called mono X, or maybe more romantically mono whatever. And that whatever could be jets, photons, WZs, could be Higgses. It could just be anything in the standard model. Everyone, almost every single one of these X's has been looked at by someone. And each of these different X's gives you, different information about the process. For example, monojets tend to be quite model independent. For example, I could have a jet radiating off the initial particle here in ISR, and that's mainly independent of whatever's happening inside this blob. So regardless of what's happening inside that blob, I know there's going to be a monojet signal, or at least some large contribution to it. However, something like mono-Higgs, the Higgs is mainly going to be radiating off of whatever's happening inside this blob. So if I see signal mono-Higgs, I can start to tell you a little bit about what dark matter actually is, and more than just saying that it's there. One nice thing about colliders is that it's obviously independent of your astrophysical uncertainties. So it's a very nice source of complementarity amongst all these probes. So next is direct detection, and it tends to be the most constraining because we've just collected so much data and have so many experiments on it. So typically, what this looks like is I'm waiting for dark matter to scatter off of some nucleus. And bounds from this are always going to be slightly model dependent. For example, if my dark matter just doesn't interact with quarks or with nuclei, then I'm not expecting to see a signal like this. For example, it could be leptophilic in that it really likes to interact with leptons, like electrons. So I might be able to use the same experiment, but I'm looking for something different. I'm not looking for recoil in nuclei. I'm looking for recoil on electrons. And so there's other caveats as well. For example, maybe dark matter comes in and scatters, but it's not the same dark matter. Maybe there's something else in the dark sector that is produced. And in the right mass ranges, this can avoid many of the dark matter direct detection constraints. And then there's all these classes that practically have no coupling to nuclei, anything that we could really see and really produce a large amount of recoil in a nucleus. For example, like axion searches, or if my dark matter were sterile neutrinos, direct detection isn't really going to probe that space very well. One drawback from direct detection is that it's also sensitive to the local dark matter density, which isn't really well known. And so there's always going to be some assumptions on what we think the local density of dark matter is. So there's some possibility that we just live in a pocket of the galaxy where the dark matter density is really low, in which case direct detection isn't really going to help you all that much. So also indirect detection. Here we're waiting for two dark matter particles to collide and then produce something that we can see. So it could be producing two B quarks, like in this plot here. And what we're seeing is these B quarks hadronize and produce all these photons. And it's the photons and electrons that we actually see here on Earth. So for example, here is some limits from Fermi, where they in particular are looking at BD bar final states. And they're looking in dwarf toroidals for the signal. Of course, there's also ways around this as well. Maybe my dark matter, instead of annihilating, decays like in sterile neutrinos. Then this depends on a different J factor, and the search just works very differently. It could instead annihilate two different mediators, like I've kind of suggested in this plot. Maybe this phi is some new mediator, which then decays into things that we see. And so the search is pretty much the same, but just these plots shift around a little bit. So that's one way to change what cross-section you're actually putting a limit on. And it could also be, your dark matter model might be multi-component. So maybe only one component is able to annihilate, in which case you're only looking at some fraction of the total dark matter density. This is also going to be sensitive to other astrophysical backgrounds and just general halo uncertainties. I don't necessarily know, if I'm looking at the galactic center, what the total halo profile looks like. And the galactic center is where there tends to be a lot of uncertainty in that respect. And so these limits are always up to how well we understand what dark matter halo distributions actually look like. And then one I want to touch on really briefly, which is closely related to indirect detection, is relic abundance. So we have a very good idea about globally, throughout the universe, how much dark matter there is. So we might try to think that in our model we can determine how dark matter was produced and how it evolved through cosmology to give us the present day density. The one that's the favorite by far is a thermal production, where at some point in the early universe my dark matter is in thermal equilibrium with the standard model. And whatever process is maintaining this equilibrium, once its rate drops below Hubble expansion, it's going to freeze out. And your current day density is going to be set by just how quickly dark matter can annihilate. So So people will often use this as a way to exclude parameter space. I am not a big fan of doing that, mostly because this is happening in very early cosmology where we don't have direct probes of, and we also don't know what the dark sector is doing. So there's lots of things that you can do in the early universe that has no effect other than to just reduce the current day dark matter density. And so I'm usually always hesitant to apply this as a hard exclusion on models. Some examples are, some examples that deviate from this normal assumption is dark matter that isn't thermally produced. Again, like axions or sterile neutrinos, where the process isn't set by a freeze-out mechanism. There's also models like FIMPs, which stands for feebly interacting massive particles. These are things that never actually reach thermal equilibrium in the early universe. So the corresponding plot would, and so they also have some coupling, but just not strong enough to reach thermal equilibrium. So generally what the plot would look like is it starts at a low density and then grows as standard model particles are able to annihilate into it. So this would grow and then be set by a freeze-in mechanism rather than a freeze-out mechanism. Okay, so for most of this talk, I want to focus on direct detection versus colliders. Since direct detection is just tends to be the most constraining, it's a good place to start when I'm trying to model build this. You know, I know there's dark matter. How can I build a model that evades my different bounds? For example, here's a plot from CMS from ICHEP just last year. Each of these orange and red curves corresponds to a different CMS search. For example, this orange one is looking at dark matter plus Z. This next red one is monophoton, dark matter being produced alongside a single photon. And then the one that tends to be the most constraining here at the bottom is dark matter plus a jet. And so they took their bounds and converted that into a direct detection cross-section. So this is the direct detection cross-section, assuming a spin-independent cross-section versus the dark matter mass. So to make this plot, they had to assume what type of interaction is the dark matter actually has. So for this plot, I believe they used a vector interaction where the dark matter has a vector-like interaction with the quarks. So one easy way that I could just avoid this is maybe it's not spin independent, or maybe it's velocity suppressed. So on the right, on the table on the right here, I have different operators. These are operators in the low momentum limit, which is useful for direct detection since this is happening at low momentum. And so on the right here are the different operators, just a basis of minimal basis of operators, and what that signal looks like in direct detection. So for example, the scalar interaction has a spin independent, which means that this interaction only interacts with essentially just the mass of the nucleon. So if you have really heavy nucleus, or you have a really heavy nucleus, then your cross section is going to be larger. However, if it's spin dependent, this means that you couple to the spin of the nucleus. So I want a nucleus with a high spin. And so if I'm looking at something with a low spin but a very high nucleon mass, then my spin independent limits are going to be really great. And my spin dependent one is going to be really poor. So at the moment, because there just aren't many nuclei that have very large spins, or there aren't many nucleons that have a very large spin, the spin dependent bounds tend to be about 10 to the 5 weaker than spin independent. So with that in mind, one easy way to avoid these constraints, or really just to make colliders much more important than they are here, is if, so let's say that dark matter is Majorana. If dark matter is Majorana, then this operator here, this vector operator, is identically 0. So in my theory, the next most important operator is going to be this one here, which has an axial vector coupling. And that's spin dependent. So if I were to remake this plot for something that's Majorana, these curves, this curve, the direct detection curve, is going to shift up by 5 orders of magnitude. And what I'll see is that, right, so this goes 10 to the minus 5, then move 10 to the minus 40. I see that colliders really set the only limit for such a model. And so that's one way that one very trivial way to avoid bounds like this, or even just a way to make colliders much more important for your analysis. Any questions on this? This is something we'll return back to quite a lot, so it's useful to understand. Okay, so with all that in mind, I want to, my game plan here is to make colliders more relevant for a search. Or in other words, I want a way to suppress direct detection bounds. And one way that I can do that is if dark matter only interacts with tops. So for the moment, let's look at a model, or pretend that such a model exists. Dark matter only interacts with tops. Let's forget gauge invariance, because that's probably not important. That's a joke. Gauge invariance is super important, but let's just pretend it's not the case here. So if dark matter only interacts with tops, then I still have a monojet-like signature at colliders, where I'm just radiating a gluon off of my initial state. However, in doing so, I also see that there's this other process here, where I have gluons coming in, and coming out is dark matter, but now two tops. So I have a much more specific signal that I can go look for. It's, if we saw something here, it would be more of a smoking gun than seeing it in monojets. Now for direct detection, this is the thing that really suppresses things at direct detection, is the fact that now my only operators are loop level. Right? There's no tops inside a proton. So if it's only loop level, then this is going to be highly suppressed. So there's two types of operators that you mostly want to worry about. The first one here, I'm just closing the loop, and I'm connecting to the nuclei versus a gamma or a z. And this is going to give you a vector operator, which if you remember I told you is spin independent. It's also not velocity suppressed, so in principle it could be really big. There is one weird thing I'm telling you here, is that I have a T-channel photon. Right, I'm expecting that this go like 1 over the momentum. So I would normally expect that if I have some interaction that's mediated by a photon, this should go like 1 over t squared. Or sorry, this operator should go like 1 over t. The other thing that's kind of weird about me writing down an operator like this is that I have a vector coupling to dark matter, which is not charged. Dark matter can't have an electric charge. And so I would expect there should be no loop level that gives me a vector coupling between a photon and my dark matter. So if you're suspicious of me writing this down, you should be. So maybe I'll write something on the board. So I'll still generate an operator like this, and let me explain how that happens. So first of all, just for the photon, the operator that I'm generating looks like Can we see this? So this is.
Could you please
Do you know which one it is?
We'll find out. So as he's doing that, this is called a charge radius operator.
Thank you.
So can we see this? Great. So this is called a charge radius operator. So this is gauge invariant, so it's not violating electromagnetism. It's not giving me a charge for my dark matter. So everything is good. The other thing you notice that there's a factor, there's an extra factor of momentum coming into this coupling. So this coupling goes like 2 powers of my transfer momentum, which cancels against what I would normally expect to be the 2 powers of momentum in the denominator. So my photon here is still generating something that goes like 1 over a constant with units of mass squared with a vector-vector interaction. Does that make sense? On an interesting note, not super relevant for anything I'm going to talk about later, but I thought was interesting, is you can write the same thing except putting a gamma 5 next to that gamma mu. And this would be the operator that you would expect for Majorana, since I can't write down this combination for a Majorana fermion. And this is called an antipole moment. So it's something that's kind of unique to Majorana fields. Okay, so the second operator that I could think about, or the second loop that I could think about, is closing this loop and radiating off gluons. And we know that there's gluons inside protons, so this could be relevant. The first important low momentum operator that such a loop generates is a scalar-scalar interaction. So for example, this is, you might expect a scalar interaction because most of the mass of a nucleon comes from the gluons. So if I have two gluons here, I should expect something that looks just like a mass term, mass term for my nucleus, or for my nucleons. Okay, so those are the things that I'm trying to shoot for with building a model like this. So let's actually look at what types of models produce something that looks top-philic. The first one is if I have a S-channel scalar. So this means that it interacts with two dark matter fields and two quarks. This is called S-channel because the mediator is produced, or this produces an S-channel process at the LHC. I have two protons coming in, my mediator, and then dark matter. So I would expect this to be top-philic because the only way that I can write down such an operator is if this phi is mixing with my Higgs, or plays some role in the Higgs sector. And since if it's mixing with the Higgs, and the Higgs has couplings that go like the Yukawa, then I expect that the field with the largest Yukawa is the most relevant. And that happens to, of course, to be the top. So this scalar interacts with all of my quarks in principle, but its coupling to the top is much larger than for any other quark. So therefore, my dark matter also interacts with tops much more than any other quark. So for direct detection, I'm mainly looking at these two operators. Right, this one is the loop level one that I was just telling you about. It produces a scalar type interaction. And I'm also going to generate things like this at tree level where I have a highly suppressed, right, a Yukawa suppressed coupling to my light quarks. And this tends to not be very important. Actually, sorry, I take it back. For the scalar, this tends to be on par with this loop level coupling, even though these are highly suppressed. I could also look at a pseudoscalar. Same reasoning applies. If it's going to be coupling the quarks, I expect that this has something to do with the Higgs sector, and this is going to couple like the Yukawa. So this, again, is going to give me a dark matter that mainly couples to tops. Colliders don't particularly care whether I'm looking at a scalar or a pseudoscalar. The process looks the same. The widths in the cross-section changed by just order one numbers. So colliders are pretty much the same for this type of model. However, direct detection and indirect detection is very different between scalars and pseudoscalars. So for example, at direct detection, I produce a spin-independent interaction, so this could be quite large. For pseudoscalars, however, this is spin-dependent, so this is weaker, the cross-section is weaker by about 5 orders of magnitude, and it's also suppressed by the transfer momentum to the fourth. So it's a very big suppression. So later when I'm talking about pseudoscalars, I'm not going to talk about direct detection at all. Limits from direct detection are orders and orders away, orders and orders of magnitude away from being relevant against other probes. However, for indirect detection, scalars are p-wave, which means that this process goes like b squared. And even in the galactic center, dark matter is still moving quite slow, so this b squared is still a large suppression. So in principle, indirect detection is not overly important for the scalar model. But for pseudoscalars, this is S-wave. So it's not suppressed by any factors of velocity, and in principle, this could be relevant for our search. The last model I'm going to talk about is T-channel. So this is a type of interaction where I have some colored scalar, which I'll call phi, and it interacts trilinearly with a quark and dark matter. So it's called T-channel because at a collider, this operator would normally generate, this is one way that you would generate dark matter at a collider is with a T-channel scalar. However, for a top-philic model, right, since I can't have any tops in the initial state, I'm not going to generate any T-channel process. So I'm going to call it T-channel for us, even though it's kind of a misnomer.
But top-filling model, you can have a T-channel, like you can have two top plus missing energy. That's the T-channel. Gluon comes in, two top and T, and then.
Exactly.
Like
yeah. For this model, that will be the process. It is T-channel, but like the reason why people call models like this T-channel is for I mean, it's just a different diagram. If that makes sense.
So, but that also constrains your top filling model should. I don't know. I've never checked that. So, have you checked that diagram? Two gluons comes in, two tops. Like it's a stop-like signal. Two tops.
Exactly. And yeah, in fact, that is so. When I'm going to talk about colliders for this model, it's going to be that process that I care about.
Two tops.
Yeah. Yeah, I'm not going to talk too much. I won't mention monojets for that signal, just because it's loop suppressed. Right. So this is the operator. This is the diagram that you're talking about. So so in the top-philic limit, I don't care about this diagram. It's really just the strong production of my scalars. And that's interesting because the cross-section for producing these mediators doesn't depend on this coupling G. So I can straight away exclude large parts of parameter space because the only thing that's limiting it is the strong coupling, which is fixed. And then for direct detection, when I close this loop, it's going to be mediated by a gamma or a Z. So there's another diagram here where there's a top there. I'm just exchanging the phi in the top in this diagram. So there's two diagrams that contribute. So the one I'm mainly interested in is going to be when this scalar transforms just like the right-handed upwards, just like the right-handed top. So it's colored, it doesn't have any SU2 quantum numbers, and it has a charge of a hypercharge of 2/3. Right, so one reason why you might think, right, so this doesn't tell me necessarily if I write this down that it's going to be top-philic.
So this is interesting. So you have an interesting monojet signal, right? So it's a color 3 object. So you cannot produce it. It's a colored object. You should produce it directly, like a S channel, and then it will decay to a quark and a jet. So your jet, you will see a Jacobian like a monojet signal.
So I can't produce
Phi directly.
a single phi.
Oh, you cannot produce a single phi somehow. So what's the charge?
So it's colored, but it's a scalar.
Scalar. Yeah. Okay. That's. So you can produce a pair.
A pair of the mediators?
It's a pair of the phi.
Yeah, exactly.
And each also 2 jet plus missing.
Yep. So when I'm looking, right, so one way that people talk about T-channel is they assume that the coupling between dark matter and all of my quarks is the same. Dijets is going to be usually the thing you're looking at. But since I'm mainly interested in tops, you have much more power if you know the thing you're looking for. Those two jets, those two things coming out are tops. These are just like the normal stop pair production limits that we're used to seeing.
Also, glue phi square, right? There should be some coupling.
Where I'm like radiating off a gluon like this or off the.
Yeah, 2 glue pair of phi. Right? There should be something 8 cross 8, 3 cross 3. So there should be some glue square phi square.
Right. Wait. Sorry. Isn't that this?
Oh, so that's the number.
Yeah.
So that's another production. I did not see that.
Oh, sorry. Yeah. Yep. Right, so this alone doesn't tell me that I might be interested in something that's top-philic. In principle, each of these G's, the one that couples to all the uptype quarks, could just be the same, and that's obviously not top-philic. However, if I make the up partner or the charm partner very heavy, then this thing that looks like the top partner is the only thing that I care about. So that would be top-philic. The other way that it might happen is if the couplings for the up in charm are just very small. So this, such that the coupling to tops is just much larger. And one regime where you often see this is in collider studies of the MSSM. If they're trying to explain naturalness, then they're going to have the stops, which look identical to the thing that I'm calling phi here. They're going to have light stops and heavy, all the other squarks are in principle quite heavy. This helps you evade constraints while making sure that you're getting a natural model that explains the hierarchy problem. So that's one regime where this naturally, for theoretical considerations, would
phi
look
is not a
top-philic.
baryon, right? So there is a baryon violating. Because you say U and chi, U as a baryon number. So phi is not a, just I'm asking, like the model you have chosen, phi is not a, it doesn't have a baryon number. So I'm
it
just
should.
saying that naturally you can have a baryon number.
Yeah, it should.
Well,
but,
it's up to you. If you give it a baryon number, then if observing, if it's not, then your model has an additional feature.
Sure, yeah. So if I want this operator to respect baryon number, or then phi better have a baryon number as well.
Because it doesn't do anything bad, because proton doesn't decay, because it doesn't couple to leptons. But baryon number violation can be useful.
Yeah. Yeah, that's true. So in a more general context, this is also going to be the case for any other models that's looking at naturalness. Like anytime I have a colored stop partner, it's going to end up, if I'm trying to add dark matter to that model as well, it'll most often look something like this. In which case, it's going to generically look top-philic if I want to avoid constraints while still explaining the hierarchy problem. But I want to be more general than Susie, right? I don't want this coupling to be fixed by gauge couplings or by Yukawas. I'm just going to treat this as a free parameter that I can play around with. So one other way to, this is the exact same model, but just another way that you might generate this. But let me make one note on here before. So notice that I have some family structure here. For each one of the up-type quarks, I have a scalar. I could move these family indices around. Instead, I could have just one scalar and 3 different types of chi. So if I just move all my flavor indices over to dark matter, I'm now looking at something that is often referred to just as flavor dark matter, where it carries some flavor charge, just like you might expect in flavor models. So if I'm trying to avoid flavor constraints are usually going to be generated by off-diagonal couplings. So here I've been kind of suggestive. I'm allowing this scalar to couple generically between any of the ups and any of my chi's. So just written like this, it could violate flavor constraints very badly. So I'm going to go to a limit where people usually call this minimal flavor violating, and just to avoid constraints, if I make all of my masses, so in this case I'm referring to the mass of my chi, or on the previous slide the masses of my phi's, and their couplings to dark matter, if I have them all be diagonal, then you should be fine. There's not going to be any flavor violation if there's no way to violate it. I mean, it sounds trivial, but that's exactly what it is. In a more general context, right, if I have diagonal matrices, there's nothing that protects me from generating off-diagonal ones. Right, as I rotate from the gauge to the mass basis, I'm going to be, those rotation matrices also act on this G. So what may have been diagonal on one basis isn't any longer. And one way that you can protect yourself from generating those off-diagonal pieces is, instead of it being just diagonal, is to make your couplings and masses proportional to the identity. So for the coupling, I'll call it alpha. For the masses, I'll call it M0. As I rotate an identity matrix, it's still an identity matrix. And I can also have it also be proportional to the square of the Yukawa matrices. If there's some flavor symmetry between dark matter and the uptight quarks, then this combination is going to suppress the off-diagonal terms. Right? Does that make sense? Okay. So normally your Yukawas, right? They're rotated by two different matrices, the left and the right rotations. But this combination is only rotated by right and right dagger. And so this will prevent you from generating large off-diagonal pieces. Also notice that if I have beta and delta M be negative, oh, well, okay, before I say that. So also notice that this generically is going to have a hierarchy between the couplings to tops and the couplings to up and charm. Right, since the Yukawas and up and charm are so close to each other compared to the top, their couplings are generally going to be quite similar, as is their masses. However, the coupling to tops and the coupling, or in the masses of the top partner is going to be quite different. So if delta M is negative, then the top partner should be quite a bit lighter than the charm and up partners. So that's one way for you to look at minimal flavor violation and generate something in a very easy way that looks top-philic. So models like this are usually called top-flavored dark matter. There's an example of one here. Okay, so just a summary.
But this does not have any signal in kind of classic flavor violating details.
Right. Well, okay. So what about like the coupling between Z's and ups and?
T2C gamma probably something like that.
Yes.
So there is.
Yeah. Yeah. So it's not coming from FCNCs.
Yeah.
It's coming from like tops to photons and Z's.
Yeah, T2C gamma or T2C.
Yep. Okay. So just a summary of the models concretely what models I'm going to look at. I'll look at a scalar that only couples to the uptight quarks. And I'm also going to assume that these couplings are the same just as a benchmark assumption to do calculations in. I'm going to do the same thing, but instead with pseudoscalar couplings. And lastly, I'm going to look at a colored scalar, where here I'm just going to assume that it only couples to top. You look skeptical.
No.
Okay, all right, great. In general, if I have something mixing with the Higgs, I'm also going to generate couplings to W's and Z's and down quarks and leptons. But for example, in two Higgs doublet models, there's ranges, there's values for the mixing angles where I don't get couplings to Z's or I don't get couplings to tops. And there's many different variations of two Higgs doublet models. So for just simplicity, I'm going to assume that it only couples to uptight quarks.
So for indirect detection also these models are interesting, right? Because ttbar will produce lots of tokens, probably similar to your D and W. Right?
It's not very constraining though, because when dark matter annihilates to ttbar, there's a large mass range where that doesn't happen.
Yeah.
So I'm only looking at
between 400 to 1 TeV.
That's right.
So
yeah.
the line would be similar to D and W.
Yes. Yeah. That's right. And in fact, that constraint depends even when I try to calculate or try to get limits on indirect detection. BB bar is the only thing that they look at in most of these Fermi papers that's relevant for me. So there's some converting that you have to do between BB bar and the hops.
Also, WW should contribute. WW also is not that bad. Similar to BB bar. So I think basically you need to look at the net photon production.
Sorry?
Net photon production from ttbar.
Right. Yeah.
So you're just a question. Since you looked at it, so is it similar to BB bar or
The WW?
like ttbar?
Yeah, the constraints are similar. I mean, so if I'm producing BB bar and TT bar at the same energies, so the same square root s, the number of photons that come out is comparable. Yeah. Okay, so for the collider search, and this is actually the paper we're putting out, this is the bulk of the work goes into doing an honest recasting of all these different stock-related searches. So at CMS and Atlas, there are three in each that we chose to do, and this is, right, so their analysis looks at producing 2 stocks, which will decay to a neutralino, which for us is our dark matter, and then it decays to a top. And this top can go hadronically, or it can produce something with a top, or sorry, something with a lepton. So that gives me 3 different combinations. The final state could have no leptons, it could have 1 lepton, or it could have 2 leptons, charged leptons. And so a lot of our work is just reproducing these different analyses. And these tend to be quite constraining. So here this is the dark matter mass, the neutralino mass versus the stop mass. And this whole range is excluded. So these are the 0 and 1 lepton analyses from CMS. And this goes all the way up to nearly a TeV. It's about 900 GeV. So we expect this to be quite constraining for our model as well, especially since our model looks identical to this. They also look at really the other model that we're interested in as well, which is either a scalar or a pseudoscalar. The final state here is ttbar, just like it is here, ttbar plus missing energy. Right, so we'll also try to map onto sigma regions that are geared towards producing models like this. Okay, so let's actually start talking about results. So for the scalar model, the ttbar+MET, let me explain these plots. So this is the dark matter mass versus the mediator mass. And the values here are the coupling G. So this tends to be most constraining when the scalar is on shell, so in the lower half of this plane. If that scalar is off shell, then you're going to be suppressed by the off shellness of that process. Whereas on the right plot here, I have direct detection. Direct detection pretty much everywhere is still constraining. It's still more constraining than the collider search. Right? These are couplings like 0.1 up to 0.9 on this plane, whereas here these vary from 0.7 down here to 2, nearly 3 at the edge of this plot. So even if I'm looking at something that's top-philic, direct detection pretty much kills me everywhere, except for in this very low region here where my dark matter just isn't heavy enough to produce much recoil energy in my detector. So I'm below the direct detection threshold. That's really the only place that scalars win out. For pseudoscalars, keep in mind here that direct detection is highly suppressed. So the next relevant thing is indirect detection. The limits from colliders are almost the same. Things moved around a little bit, but generally it's a very similar, very similar couplings. For indirect detection, in this lower half of the plane, you're not getting any constraints whatsoever. So the reason for this is because if I try to increase my coupling, the width is going to get larger. And even though this is, right, so the width is going to get larger, and as that width grows, it's going to further and further suppress, this annihilation process. So even if I increase the coupling a lot, at some point this process is independent of the coupling. Of course, by that point, you're violating unitarity, but the point is that in this area, you're not making any constraints. So everywhere here, collider is always going to be dominant. And the reverse is true when I go either on resonance, here along this line. If my process is resonant, then indirect detection is going to be more constraining. And then the other place where this in principle could be more constraining is at higher dark matter mass. So once I get up here, I'm able to annihilate to 2 tops. And up here, I'm always going to be more constrained by indirect detection than by colliders. So here, there's a nice sense of complementarity where one is strong, the other is weak, and vice versa. lastly is with the colored scalar. Remember, my production mechanism is just the strong. It's just the strong process. So it's independent of the coupling I choose. Just as long as my dark matter is light enough to actually, is light enough such that my top partner is able to decay. So what I see here is the direct detection limits. And then this red line is the exclusion curve from colliders. So everything inside this red curve is going to be excluded, which is really powerful. This is ranging from 200 GeV to nearly a TeV for my mediator, ranging over 400 GeV for my dark matter. So this cuts out a big part of parameter space that direct detection says would normally be fine. Any questions with this plot? Okay, so lastly, there was an excess seen presented in the ICHEP set of analyses. So this is coming from the Atlas 1 lepton search. There's a signal region here called DM low. This signal region was intended for what they call a dark matter model, which is what I'm calling the scalar model. So their final state is ttbar plus an on-shell scalar. And DM low here, low just means that it's looking for a lighter set of scalars, so maybe around 100 GeV. So they predicted from the standard model there to be about 17 plus or minus two events. However, they observed 35. So this is about a 3.3 sigma excess, which if you're a particle physicist, you're going to be very excited about. The nice thing about this too is that the other Atlas searches don't rule it out. 1 lepton, because of the high branching ratio of tops to jets, backed against a very clean lepton to reconstruct, 1 lepton tends to be the most constraining. However, CMS doesn't see this in their 1 lepton. So their expected and observed is very close. And so you might worry that CMS alone excludes this. So right, there's 28 events here to explain. And these two signal regions look very similar. The only thing that differs is that Atlas cuts on AMT2, CMS cuts on MWT2. They're not exactly the same, but they're similar. But maybe you might hope that there's some very weird fine-tuning that allows you to evade these cuts, but get your events into the signal region. It turns out that's not the case. These two variables are very highly correlated, and pretty much all the events that would end up in this signal region are also going to end up in this signal region. So if you do a full analysis and combine all of these, all 6 of these analyses together, you can look in a global way how significant this really is. So in this plot here, I have my dark matter mass versus my stop mass, and these different lines correspond to how many events I can fit into DM low. So of those 18 events, how many could I explain? This blue curve here corresponds to it corresponds to the excluded region from this global analysis. So everything inside this blue region is excluded. So if you look closely or come closely and look at this, you'll see that at the edge of this excluded region, I can only explain about 10 of those 18 events. Everything out here is going to put fewer events into DM low. So at most, you can explain 10 of those events in DM low. And a naive combination tells me that this 3.3 sigma is really reduced to 2.3, which is nice, and I'll keep an eye on it, but it's not necessarily something to be excited about. So these analyses are very shortly going to be updated. Some of them are already updated at Morion, but we're just waiting for the last couple to come out. The Atlas 1 lepton is not out yet, so I can't tell you if this excess is gone, but we're expecting it to either be gone or severely reduced. Okay, so lastly, working in dark matter can be very depressing. You're looking at direct detection limits that are getting worse and worse. So you might wonder, are we ever going to discover it? But don't despair, there's a lot of pheno to do. There's a lot of models that people haven't looked at, and there's lots of caveats that people just assume. So there's still a lot to play with. Top-philic models, they're well motivated. They help you evade some of the strongest dark matter constraints. And I think that it's something to look forward to with these new updates from Morion. And lastly, keep an eye out for our paper. It'll be coming out in the next few weeks. It's going to include the updates from Morion, And dark matter isn't the only purpose of the paper. So this is going to have a larger recasting. It's a larger recasting effort than just in terms of dark matter. So there's lots to look at in these analyses. All right. Are there any questions?